Welcome to this comprehensive guide on optimizing garbage collection in Unity 3D using Visual Studio, a critical skill for maintaining smooth and responsive game performance. Understanding and managing garbage collection is paramount for any serious game developer aiming to deliver a high-quality user experience without performance hiccups. Frequent and poorly timed garbage collection cycles can lead to noticeable frame rate drops and a choppy gaming experience, even if your average frame rate appears high. These momentary freezes, often referred to as GC spikes, can severely disrupt gameplay flow and player immersion, making optimization a necessity. Since C Sharp automatically handles memory management, developers need to understand how to effectively work with and around the garbage collector to minimize its impact on game performance. This involves learning the underlying mechanisms and applying specific coding practices to reduce the GC's workload. Let's begin by understanding the two primary types of memory allocation in Unity, the stack and the heap, which are fundamental to C Sharp memory management. A clear grasp of these concepts is the first step towards effective GC optimization. The stack is a small, fast memory region primarily used for local values within a function, such as primitive types like integers and booleans and method parameters. It operates on a last in, first out, or LIFO principle, making it highly predictable and efficient for temporary data. Memory allocation and deallocation on the stack are extremely fast and automatic, as the memory is cleared immediately when the function ends, making it highly efficient. This automatic cleanup means stack allocations never contribute to garbage collection overhead, making them ideal for short-lived data. Conversely, the heap is a much larger, more flexible memory region used for objects that are too large for the stack or need to persist beyond the function's scope, such as class instances. Unlike the stack, heap memory is not automatically deallocated when a function exits, requiring a different management approach. Memory allocation on the heap is managed by the garbage collector, which periodically identifies and reclaims memory from objects that are no longer referenced. This process, while essential for preventing memory leaks, can introduce performance spikes if not carefully managed, as it pauses your application briefly. Now, let's explore several practical techniques to mitigate the performance issues caused by garbage collection spikes in your Unity projects. These strategies will help you write more efficient code and reduce the frequency and duration of GC pauses. Our first technique is to avoid unnecessary allocations, which directly reduces the workload on the garbage collector. Every new object created on the heap contributes to the GC's work, so minimizing these allocations is a primary goal. Consider using structs instead of classes for temporary objects whenever possible, as structs are value types allocated on the stack, thereby avoiding heap allocations and garbage collection. For example, a vector3 is a struct, and creating many of them won't trigger GC, unlike creating many instances of a custom class. Another crucial tip is to cache objects and reuse them instead of creating new ones every frame, especially within Unity's update or fixed update methods. For instance, instead of calling getComponent rigid body every frame, get the reference once in awake or start and store it in a private variable. Be particularly cautious with string manipulation, as strings are immutable in C Sharp, meaning every modification creates a new string object on the heap. Operations like string1 plus string2 or string format can generate numerous temporary strings, leading to significant GC pressure. Instead, use string builder for concatenation to minimize allocations, as it modifies a single buffer in memory. This is especially important when building complex strings within loops or frequently called methods, as it drastically reduces temporary heap allocations. Avoid boxing and unboxing, which occur when converting between value types and reference types, as these operations create temporary heap allocations. For example, passing an int to a method expecting an object will box the int, creating a new object on the heap. Finally, have APIs take a target collection as a parameter instead of creating new collections within the method, allowing you to reuse existing memory. This pattern, often seen with methods like physics.overlaps non-alloc, prevents repeated heap allocations for temporary lists or arrays. Object pooling is another powerful and widely adopted technique for frequently created and destroyed objects, such as bullets, enemies, or visual effects. This pattern is a cornerstone of performance optimization in many game genres. This involves pre-allocating a collection of objects at the start of your game and then reusing them as needed, rather than continuously instantiating and destroying them. When an object is no longer needed, it's returned to the pool instead of being destroyed, ready for its next use. Object pooling drastically reduces the need for continuous allocation and deallocation, thereby minimizing garbage collection events and improving performance. By avoiding instantiate and destroy calls during gameplay, you eliminate a major source of GC spikes. Unity itself introduced generic object pool solutions in 2021, simplifying the implementation of this pattern directly within the engine. The Unity engine Pool.ObjectPool T-Class provides a robust and easy-to-use API for managing object pools, making this optimization more accessible than ever. For more advanced control over memory, you can use the Unity engine Scripting.GarbageCollector API to manually time garbage collection. This approach offers fine-grained control but comes with increased responsibility for memory management. This API allows you to disable automatic garbage collection and then manually invoke it at specific, less performance-critical times, such as during scene transitions or loading screens. By calling GC, collect only when the player won't notice a brief pause, you can smooth out gameplay. However, disabling automatic collection requires careful management to avoid running out of memory, as you become solely responsible for memory reclamation. If you fail to manually collect garbage, your application's memory usage will continuously grow, eventually leading to crashes. For highly advanced scenarios requiring ultimate performance, consider using unmanaged memory allocation. This technique bypasses the C-sharp garbage collector entirely, giving you direct control over memory, but also demanding meticulous management. This involves using native collections like native array, T, spans, the Stackalot keyword, and fixed-size buffers to allocate memory outside of the garbage collector's domain. These tools are part of Unity's Burst compiler and job system, designed for high-performance, data-oriented programming. Be extremely cautious when using Stackalot, as stack size is limited and excessive allocation can quickly lead to a stack overflow exception, crashing your application. It's generally reserved for very small, temporary allocations within a single function scope. Profiling is an absolutely essential step for identifying memory-related performance bottlenecks and validating your optimization efforts. Without profiling, you're essentially guessing where your performance issues lie, which can lead to wasted time and ineffective solutions. Unity's built-in profiler is your primary tool for monitoring CPU, GPU, memory, and rendering performance in real time. It provides a wealth of information, allowing you to pinpoint exactly what's happening under the hood of your game. Pay close attention to the CPU usage section to identify scripts consuming excessive CPU time and the memory section to track memory allocation patterns and identify potential leaks. Look for sudden spikes in GC, collect, or GC, alloc to spot problematic areas. Always profile your game on target devices to obtain accurate performance data, as editor performance can differ significantly from a deployed build. What runs smoothly in the editor might stutter on a mobile device or console, so real-world testing is crucial. Visual Studio's memory usage tool is equally invaluable for monitoring your app's memory use and finding the root causes of memory issues within your C# code. It offers a deeper dive into managed memory than Unity's profiler alone. This powerful tool provides real-time charts, allocation rates, and garbage collection activity, allowing you to take and compare memory snapshots at different points in time to pinpoint leaks and inefficiencies. By comparing snapshots, you can see exactly which objects are accumulating in memory. Beyond specific GC optimizations, several other general optimization tips can further enhance your game's overall performance. A holistic approach to optimization often yields the best results. For asset optimization, reduce texture resolutions, use compressed texture formats, and remove and use channels from meshes to minimize memory usage. These small changes can collectively free up significant amounts of GPU and system memory, improving loading times and overall performance. Utilize asset bundles to load game assets at runtime, which significantly reduces initial loading times and overall memory usage by only loading what's needed. This modular approach is particularly beneficial for large games with many assets, allowing for dynamic content delivery. For code optimization, always cache variables, reduce redundant function calls, and avoid unnecessary calculations within performance-critical loops. Simple practices like storing a component reference instead of calling getComponent repeatedly can have a major impact. Coroutines are excellent for spreading computationally intensive tasks over multiple frames, preventing single-frame performance spikes and maintaining a smooth frame rate. Instead of doing all the work at once, a coroutine can yield control back to Unity, distributing the load. Optimize physics by setting a fixed time step, manually controlling physics simulation, and using simpler colliders whenever possible to reduce computational overhead. Complex mesh colliders, for example, are far more expensive than primitive colliders like spheres or boxes. For graphics, optimize settings, use level of detail management for 3D models, and batch similar objects to significantly reduce draw calls. LODs ensure that distant objects are rendered with fewer polygons, while batching combines multiple small meshes into one, reducing CPU overhead. Bake lighting to reduce real-time light calculations, simplify shaders, and consider shader LODs for varying detail levels based on distance or performance settings. Baked lighting is pre-calculated, eliminating expensive real-time computations during gameplay. Finally, implement occlusion culling to prevent rendering objects that are not visible to the camera, saving significant rendering resources. This technique works by determining which objects are hidden behind others and skipping their rendering entirely, improving GPU performance. By diligently implementing these garbage collection optimization techniques and effectively utilizing the powerful profiling tools available in Visual Studio and Unity, you can dramatically improve your Unity 3D game's performance and deliver a smoother experience. Consistent application of these strategies will lead to a more polished and enjoyable game. Thank you for watching this guide on optimizing garbage collection. We hope these insights help you create high-performance Unity games. Remember, continuous profiling and iterative optimization are key to maintaining excellent performance throughout your game's development lifecycle. Happy optimizing!